All right, welcome back. This video is going to be going through something which you need, which is covered in the second lecture, okay? And you'd find questions on this at the start of the third lecture as you start off your third lecture. You find a lot of questions on this asking about aromaticity and these other things. So, what is this video about? It is about, and here we're going to be classifying your organic compounds. Remember that you're going through organic chemistry, which is the chemistry of carbon, right? Now, it's big, it's huge. It has a lot of things, right? We saw that there are millions of compounds that have been found. So to make the job easier for us, and more compounds are found every year, by the way. So the number keeps growing. So to make the job easier for ourselves, we group them according to some characteristic they have, right? One easy way to group is using their functional groups. And you're going to be using that a lot, right? Throughout the whole course. That's how you'll be studying their reactions. You'll be studying them according to their functional group. To say, okay, the functional group tells you the family, right? The homologous series. So if they are alkanes, that's the family, the homologous series. So you'll be grouping them according to their families, right? But what you used to know that it belongs into that family is the functional group, right? So we use the functional group to tell their families. That is where we have alkanes, alkenes, alkynes, carboxylic acids, ethers, esters, the list goes on. Alcohols, phenols, whatever you want to do. Now, in here, we are not really classifying according to that. We are still doing the same thing, but we are not classifying using the family names, the homologous series. Homologous series is the family. A homologous series is a family, right? Like alkanes, alkenes. We're not going to be using that. Here we're going to be classifying using something else. You say to me, what is the importance of it? Look, the importance of classifying is it helps us, okay, when we classify things into by using certain features which they share, whatever, then it can help us to analyze some things about these things or predict. Okay, we can know we can have a general idea about their properties. We can be able to name them. Okay, we can predict properties. Like we can say, okay, everything that is saturated will behave like this, like this, like this. Looking at this saturated guy, we can know the general thing about saturated compounds. So we'll say, okay, this compound is saturated, meaning to say that it is going to do this and that, okay? Or you can also give it a name, okay? This classification we are doing here also helps us, just like the homologous series. This one which we are doing here also helps us in the naming of compounds, okay? To be able to name the compounds, to be able to guess their reactivity when we mix them with certain things, right? So this is another way of classifying. Just like using homologous series, in here we will not be using homologous series, but we'll be using features, what they look like. Not only the reactive part, but what they look like in general. All right, so that is what we're doing. We are classifying or grouping our organic compounds using a certain feature. So let's go through this grouping, and there are parts that I want you to make sure you don't miss. Okay, let me choose this crayon. So let's go through that. Well, our organic compounds generally are split into two major categories using this method of classification. We are not using the homologous series. We are using this method that we are using. It has two methods, and I'm zooming out so that you can see. It has two main groups. All the organic compounds, we group them into two main groups. And one is called open chain. Okay? Open chain. And when we say, let me make it smaller, when we say open chain, we can also say acyclic. Acyclic, open chain, or you can also see it say aliphatic. It's the same thing. And when we say we have an open chain or an aliphatic compound, an open chain compound, listen to this, open chain. Open chain. On the other side, we'll have a closed chain, okay? Open chain is when you cannot go in a complete loop from where you started and get back there, right? You can have something go around in circles, blah, blah. Okay, this is an example. If I start moving continuously, let me choose like a red or yellow, green, whatever, a highlighter. If I start moving from this Okay, I hope you can see. I'm highlighting. Surely you can see. Let me use light blue. If I start moving, oh, light blue is the same as what I've written. Put red. If I start moving from the first carbon going to the second, I'm highlighting, going to the third, I can't go back. There's no way for me to go continuously back to the first. Okay, I've gotten to the third, but I can't go back to the first. I'll end here. So it's an open chain. A closed chain will give you a way back, a link back. All your carbons will be linked. So you can go around and get back where you started. So we have two main groups, major groups. Okay, there's something I want you to see here, so make sure you are listening. You have aliphatic or open chain or acyclic. Remember the names: aliphatic, open chain, or acyclic. Acyclic, open chain, aliphatic. This is the compounds that are open. They don't take you back where you started, in simple terms. Okay, and when you do those type of compounds, we just break them down into two, which is saturated and unsaturated. When we say saturated, if we have a saturated solution, we are saying there is no more space, right? Everything is dissolved in this solution. You can't add any more solute into your solvent. Like, you can't add any more sugar. It won't dissolve. It will just go to the bottom of the solution. Saturated is that. It means that it is full to the max. So when we say we have saturated something, in simple terms in chem, we're just saying all the carbons have done the maximum number of bonds. And we know carbon can do 4 bonds, right? So it has done 4 separate bonds. Okay? All the bonds will be single. There won't be a double bond and there won't be a triple bond. But when we have something that is unsaturated, we're saying you can see some carbons not having having some double bonds, carbon to carbon, right? Carbon to carbon double bond, and that is an unsaturated compound, right? Okay, so now what we'll be doing is, we saw that we're not really focusing on that. Our focus will be on the closed chains. But I wanted you to just remember the aliphatic. Okay, I don't want this video to last too long, so don't make it too hard. Just make sure you remember these things because you have to move with them for a long time, right? Aliphatic, open chain, or acyclic. If you forget this, and those ones, they are open, just remember the names: acyclic, aliphatic. It means open chain. Now we go to closed chain. There's something I want you to see. Now, this is the second category. Closed chain or ring, we can also call it ring, or cyclic. Those ones, we call them acyclic, right? And here we're calling them cyclic, these closed chain ones. There will be something like this. You have a carbon, you have another carbon, it goes to this carbon. Let's say you have another carbon here. Okay, the number of carbons don't matter. It goes to another carbon here, and it goes back. So can you see that there is a closed chain here? That's what all of them will do. And they're going to be easier to see on the bond line formula. Okay, the bond line formula is going to be very, very straightforward. It will be easy. So because the bond line formula, remember, it doesn't have the carbon atoms. It is like this. That is what it is. If you're not sure about the bond line formula, just check the video on formulas, right? So in here we are saying we have either open chain or we have closed chain. Okay, we have either acyclic or we have cyclic. We have either aliphatic, okay, is the same name, or we could say a ring. Now we are coming to this closed chain. This closed chain, I want you to see what's going on here. So when we have a closed chain, right, I don't want you to get lost and think there are a lot of things. There are not a lot of things. There's nothing here. On closed chain, basically we are going to separate our closed chain into 2 parts. One part is a closed chain that has only carbons in the ring. Okay, like if you look at this diagram here, there are only carbons. But what would happen? Let's say I would say carbon goes to a carbon, but this carbon goes to an oxygen, which goes back to a carbon. Now I no longer have just carbons in the ring. In the ring, there is another guy in there, right? And when there is another guy, we call it a heteroatom. Okay, and that is another guy which is not carbon, and that is what will make you have a heterocyclic. Heterocyclic, you'll be having a cycle or a ring, but in that ring there is another guy that is not carbon, and we always put it so that you make sure you see. Even if we were to draw the bond line, we'll do this, then put an O, right, and then come down like that. So something like that. So we always put the O so that you make sure you know that it's not a carbon in that corner. All right. That is heterocyclic. Homocyclic means that the whole cycle, okay, the cycle is carbon atoms only. Homo means same. Homo means the same. And what is it? What is the same? It is only carbon. So homocyclic. Hetero, different, right? Different what? There's a different atom which is not a carbon there. Now, I want you to know that this separation always ends on this stage where we now break. We've seen that we have homocyclic and heterocyclic. Homocyclic is also called carbocyclic because you only have carbons in that cycle, right? Now, I want you to know that these stages always end on here where we are, on alicyclic versus aromatic. So, I want you to make sure you know this part. Whether you are looking at homocyclic or heterocyclic, they always end at alicyclic versus aromatic. Huh? Can you see that? They always end at the comparison between alicyclic and aromatic. Okay, what is that? I'm going to make you see in the next video how you know aromaticity. Okay, I'll now be using examples on each stage, but I want you to have this picture in your head that at every stage they always end with aliphatic versus aromatic. Okay, so we'll be saying we have a closed chain because here we are talking about closed chain where we have cycles. Okay, they could have 3 atoms. Like in this case, there are 3 atoms. Or they could have 4. 4 normally would be like a square like that. All right? Carbon here, and then you link them. Or they could have 5 or 6. 5 normally is like carbon here. And then you have carbons at this corners. And then you do this, come in. You have a carbon and a carbon, and then you link them. So there are 5. Okay? You can count them as 5. So it's still a closed chain or a cycle. We have a cycle. All the carbons are linking back. It's a nice round path. Now, these ones we say they can be homocyclic or heterocyclic. If they are homocyclic, that means the whole cycle has carbon, like this one and that one. But if you bring a foreigner like an oxygen or a nitrogen or a sulfur or a halogen, halogen means the group 7, which is chlorine, bromine, iodine. If you bring them in the cycle, they are going to affect your cycle, right? And we'll say you have a heterocycle now. It is heterocyclic. Now that heterocyclic, we're going to split it into aromatic and alicyclic. Look, there we talked about acyclic. Don't confuse acyclic with alicyclic. Alicyclic is what things that are not aromatic are. So either you are aromatic or you are alicyclic. Okay, alicyclic. Don't worry about this benzene versus no benzene, because when you look at this, I'm going to show you. But I can just explain to you to say that these homo guys, there's one more step where they can just go after aromatic, okay, to say that aromatic, okay, the most common aromatic thing has benzene. It has this common guy called benzene. So benzene is so big and is in a lot of things. So we just split the aromatic guys into, do you have benzene or you don't, right? If you have benzene, we call you benzenoid. If you don't, we call you non-benzenoid. But it is on aromatic. But really where it was ending is this one, aromatic versus alicyclic. That's the last stage of both. So where do we say from closed chain? It's only 3 steps. You'll be saying we have closed chain, right? Now this closed chain in step 2, it is broken into homocyclic and heterocyclic. In stage 3, homocyclic is broken down into alicyclic versus aromatic. Stage 3 again, heterocyclic is also broken down into alicyclic and aromatic. That's done, if you know that, okay? But you know that for homocyclic, the aromatic, most of them have benzene. So we can say, do you have benzene or you don't? Benzenoid versus non-benzenoid. Done. Okay, that is like the 4th stage, which is only there for homocyclic or carbocyclic compounds. Homocyclic, they are cycles. Remember we said they are called cyclic or ring, right? Remember they're called cyclic or ring or closed chain. The other one, open chain or acyclic, right? There we go. Open chain or acyclic or aliphatic. Try to write it from your head. Let's see how far you can go. Try to put this left hand side, okay, try to write it, and you can confirm with the video again, this left hand side, and try to construct the right hand side on your own and see if you can split. So it's organic compounds that are split into these first two groups, and then the two groups keep going down and down and down. That's it. See you in the next video. Goodbye for now.